Would like to learn more about Kubernetes security? Then you guys came to the right place. I mean, when I was looking over various news articles, and I think just from experience, the way organizations are moving into microservices architecture, I think security personnel to have up-to-date Kubernetes knowledge becomes more and more imperative. So I just wanted to add an episode, or probably two even, to cover some of the components within Kubernetes, just to understand how Cloud Native Computing Foundation have developed Kubernetes. What are the ways to secure it? What are the considerations to think about? And just to have a little bit of knowledge of you know and best practices, essentially how Kubernetes should be running in your environments. Because I think a lot of, obviously, there is usually there is a disconnect between development teams or DevOps teams that create clusters, build code, and then how these components and how these microservices are running in your production environments. So we'll just cover some of the history. We'll just discover what is, first of all, Kubernetes. What are the four C's of the and four C's of the components of Kubernetes itself, and then we'll just cover some of the best practices. We'll share some of the ideas how to configure and secure them, and we'll just dive quite a bit deeper in it. So first of all, you know Kubernetes is essentially it's an open source orchestration engine, essentially, which is built for automating deployment, scaling and management of your containerized applications. So this is an open source essentially project which is run by Cloud Native Computing Foundation, also known as CNCF. So when you deploy Kubernetes, you get essentially a cluster. So Kubernetes cluster consists of a set of worker machines called nodes, essentially, that run containerized applications. So the control plane manages the worker nodes, and the pods are essentially in the cluster itself. So as you can see, just I think the image kind of clearly displays. So within the control plane, you have some components which essentially are the kind of the orchestration and management unit of the worker nodes that actually run the applications. So you have the management plane that manages the worker nodes that actually run the applications. So as you can see, in the management plane, you have components such as Kube API server, you have etcd. Actually, let me just talk through you as well. So API server essentially is the one that exposes Kubernetes API. So underneath, you have programming interface essentially that is exposed and allows communication between various parts of your Kubernetes cluster. So API server essentially is the front end of your control plane. etcd is a consistent and highly available key value store. So etcd, is used as Kubernetes backing store for all the cluster data. So it essentially just holds a number of key value pairs. Kube scheduler watches for newly created pods with no assigned node and selects a node for them to run on. So essentially, scheduler is the one that essentially does the work and schedules the pods on where they should be running, making sure, and we'll cover some of the stuff like how we can limit where the pods can run and how we can making sure that pods run in a specific place if you want to do that. Kube controller manager, so runs controller processes. So logically, each controller is a separate process. But to reduce the complexity, they are all compiled into a single binary and run in a single process. And then lastly, but not least, is Cloud Controller Manager. So Cloud Controller Manager lets you link your cluster into your cloud provider's API. And it also separates out the components that interact with the cloud platform from components that just interact with your cluster. So that's all your management components. And then you obviously have the components that run on the worker nodes. So you have kubelet. So kubelet is essentially an agent that runs on each node in a cluster and makes sure the containers are running in a pod. And then you have a kube proxy, which is essentially a network proxy that runs on each node in your cluster, and it's implementing part of the Kubernetes service concept. And then you have a container runtime. So essentially, it's the software that is responsible for running the containers. So as you can see, API server is the main interface because every single component in your control plane as well as in your worker nodes has to interact with API server. So this is the main thing. So and essentially control plane's components make the global decisions about the cluster. So as well as detecting and responding to cluster events, it consists of components such as, as I mentioned, API server and all of the rest of the components, whereas node components run on every node and they maintain pods and providing the Kubernetes runtime environment. So there we go. So let's go into the next one. So it's important when you start. So I guess, the key point, and I'll kind of dive into the 4 concepts of Cs, but the 4 concepts of Cs as developed by Cloud Native Computing Framework is essentially it covers the cloud as in an outer layer. Then you have a cluster, which obviously there's, within the cluster there's multiple containers, and then you have a code. So that's why it became a 4 Cs. So 4 Cs essentially make up your whole Kubernetes deployment. But the key point is, as you can see, it's one kind of encompasses the other. So that's where the concept of defense in depth comes in place. So we have to make sure, between the shared responsibility model, we have to make sure that every single ring is provides an adequate security, because every single one of them misconfigured potentially allows threat actors to gain entry into our clusters. So there's a few options that how and when we can deploy Kubernetes clusters. We can deploy them on bare metal, on premise, or in the cloud. We also have different deployments in the cloud where you have a managed clusters, or you have specific clusters that run on virtual machine scale sets on actual virtual machines, and we can deploy containerized applications as well. So there's a few ways how we can actually do that. So Kubernetes was designed to be highly portable, and customers can easily switch between these installations and also migrating their workloads. So all of this potential customization of Kubernetes means that it can be designed to fit a large variety of your scenarios, or what kind of use cases do you have. However, it's also its greatest weakness when it comes to security, because Kubernetes is designed out of the box to be customizable, and users must turn on certain functionality in order to secure their cluster. This means that the engineers responsible for deploying Kubernetes platform need to know about all the potential attack vectors and vulnerabilities, as well as poor configurations that it can lead to. So it becomes quite a hefty work to actually get it right and do it properly. It is recommended to harden the underlying hosts by installing the latest version of operating system, hardening the operating system, implement necessary patch management and configuration management system, implementing essential firewall rules, and undertake specific security measures depending on a data center environment. So there's a lot of work to be done, because obviously there is Kubernetes run on underlying, whether it's virtual machine scale sets, virtual machines itself, and depending where the shared responsibility model is between your cloud and your deployment of Kubernetes, you have to make sure that underlying hosts are secure out of the box, and you have to manage them. You have to patch, OS vulnerabilities. You have to scan them. You have to make sure that firewalls are set up correctly, and how the access are, gained to underlying node or to underlying virtual machine that clusters run in. So yeah, there's a lot of things to be considered. So we'll start with a few things. So Kubernetes as itself, obviously requires patching, and the way we do patching is obviously making sure we update the Kubernetes versioning. So Kubernetes versions are normally deployed every quarter. So normally you have four new versions that are deployed over a year. So it is becoming possible to track all the potential attack vectors. So this fact is unfortunate, as there is nothing more vital than to be aware and on top of potential threats. So the best defense is to make sure that you are running the latest available version of Kubernetes. So Kubernetes project maintains the release branches for the most recent 3 minor releases, and it backports the applicable fixes, including security fixes, to those 3 release branches, depending on severity and feasibility. Also, patch releases are cut from those branches at a regular cadence, plus additional urgent releases when required. So hence, it is always one of the, it's part of the security recommendation, but it's important to upgrade the Kubernetes cluster to the latest available stable version, and it's important to refer to the version SKU, and I'm going to cover this because the version SKU is essentially, it's an important aspect because, as we discussed, all of the components have their own Kubernetes version. So when you are uploading or when you're upgrading your Kubernetes cluster, not only you need to upgrade the API server, but you need to upgrade every single component within the cluster to make sure that they have to be, normally they only allow to burn one major version SKU. And what I mean to that is that they only allow to have a one difference in version. So, there are several techniques such as, rolling updates. You can do node pool migrations to allow, to complete an update with a minimal disruption and downtime. So Kubernetes versions are normally expressed as x.y.z. So where x, the first number, is a major version, y is the minor version, and z, essentially the last number, it's a patch version. So Kubernetes project maintains release branches for the most recent 3 minor releases. So normally you will know that Kubernetes is normally covered by 1.28, 1.27, 1.26. So these are the, the major version is number 1, and then the minor version is the second number. You rarely will upgrade patch versions because it just becomes too cumbersome, especially in production environments. So the Kubernetes project maintained release branches for the most recent 3 minor changes, as I mentioned. And normally they will receive a 1 year of patch support. Kubernetes 1.18 and older received approximately 9 months of patch support, and applicable fixes, including security fixes, may be backported to those 3 release branches, depending on the severity and feasibility. So patch releases are cut from branches at the regular cadence, plus additional urgent releases as and when required. So for example, Kube API server, as I mentioned. So in highly available clusters, the newest and oldest Kube API server instances must be within 1 minor version. So that means is essentially if you upgraded your API server to 1.28, any other API server instances within the cluster has to be either 1.28 or 1.27. They can't change. They can't be more than 1 minor version difference. Otherwise, it's not going to work. Also, it's important that kubelet cannot be newer than the Kube API server. So, there's a lot of documentation. I don't want to cover every single, potential SKU, but there's something very important to be aware of and to understand how different components has to be upgraded and what is the allowed difference in minor versions between the components. So you can always just jump on Google or look at between Kubernetes documentation. There is a great paper in there called Kubernetes version SKU, which essentially will answer most of your questions in that regard. Now, if we go to another part, it's important also, so as we discussed the components, all of these components are working on specific ports within your cluster. So it's very important to ensure that security to those ports are restricted to only trusted sources. So as you can see, Kubernetes clusters usually listen on a range of well-defined and distinctive ports, which makes it easier to identify the cluster and to attack them. Hence, it's highly recommended to configure authentication and authorization on the cluster and the cluster nodes. So essentially, as you can see, for example, you got Kubernetes API server normally is communicating on the port 6443. You have etcd server, client API normally is communicating between 2379 and 2380 port. You got Kubelet API that normally communicates on 10250, and as you can see the other ones, you got Kube Scheduler, Kube Controller Manager, you got read-only Kubelet APIs ports, as well as you got the worker node ports and how they communicate. So you have to make sure that intercommunication is set up properly. You can even do some of the firewall management and making sure that these communications are secured and only with the trusted sources, and making sure that there is no outside connection, for example, to your Kubernetes API server. That's very important to lock it down as much as possible. Now let's go dive deep and expand on this. So I just kind of briefly covered in the beginning what is the cloud native security 4Cs. So 4Cs essentially kind of goes deep into what is defense in depth. So we got the 4Cs, we got the cloud, the clusters, the containers, and the code. So in order to build a proper Kubernetes cluster and properly secure it out of the box, you have to make sure that all 4Cs are securely configured. They are continuously monitored with logging, with scanning, images and OS systems, to making sure that vulnerabilities is discovered as well and patched, based on specific risk cadence that you have in your organization. So essentially, this layered approach essentially augments the defense of depth approach to security, which is essentially regarded as best practice for securing software systems. So each layer of the cloud native security model builds upon the next outermost layer. So the code layer obviously benefits from strong base, so cloud, cluster, container security layers, and obviously you cannot safeguard against pure security standards in the base layers by addressing security at the code level. So obviously it starts with a base layer, it starts with a cloud or infrastructure security. So it's important, for example, if you are considering to deploying your Kubernetes clusters, as you can see, so depending on where you are securing it, where you are deploying it, we're normally going to cover here mainly cloud. We're not going to cover, on-premises Kubernetes deployment models, but it starts with securing that outermost layer, which is the cloud. So if you are thinking of deploying Kubernetes cluster, whether it's one of these clouds as mentioned here, you got IBM, Azure, AWS, obviously Google Cloud, you have to consider and look at shared responsibility model. There is a few obviously clouds as well, same as you got things like Azure AKS, you got in AWS, you got ECS, and there's a few another different cloud deployment models. So you have to understand where does your responsibility lies in terms of securing the clusters or underlying infrastructure. And obviously you have to make sure that you follow those best practices. So you start with the outer layer and then making sure that you apply security standards going into the innermost layer, which is the code. So some of the things to consider in your infrastructure security, so obviously network access to your API server, or essentially the control plane, which is the main component. So all access to your Kubernetes control plane should not be allowed publicly essentially to access it from the internet, and is controlled by network access control lists restricted to a set of IP addresses to administer the cluster. So obviously, if you are required to administer the clusters from outside of organization, then obviously you have to make sure that you build specific standards. So whether you use access control lists to allow access to a specific set of IP addresses for your administrators. You can obviously leverage even more security by deploying things like Bastion hosts and many more different things. The next part is obviously network access to your nodes. So nodes should be configured to only accept connections via the network access control lists from the control plane on the specified ports, and accept connections for servers and the Kubernetes of type of node port and load balancer. So if possible, these nodes should not be exposed on the public internet entirely. So again, try to limit that exposure as much as possible. Also, you have to make sure that Kubernetes access to cloud provider API is secure too. So each cloud provider, needs to grant a different set of permissions to the Kubernetes control plane and nodes as well. So it's best to provide the cluster with cloud provider access that allows the principle of least privilege, and that's very important. Again, principle of least privilege is making sure that we only allow permissions that they need to do their job in order to essentially to administer the Kubernetes cluster. We also need to make sure that we limit the access to etcd, or essentially it's a data store. So how we can, limit that depending on your configuration. And also we have to always make sure that etcd is encrypted. So whenever it's possible, it's a good practice to encrypt all of the data store in etcd, because etcd normally sometimes will hold a sensitive data component, sensitive data pairs that should be always encrypted at rest. So once we move away from the cloud, we get into the cluster security. So essentially, there's two major parts of concern for how we secure in cluster. So securing the cluster components that are configurable, and securing the applications which run in the cluster. So if you want to protect your cluster from accidental or malicious access and adopt good information, security practices, you have to essentially secure the components within your cluster. So depending on the attack surface of your application, you may want to focus on specific aspects of security. So for example, if you're running a service that is critical in a chain of other resources and a separate workload, which is vulnerable to a resource exhaustion attack, the risk of compromising your first service is high. So if you do not want to limit resources of service B, these are the critical sort of points to discuss and think about how we can secure your clusters. So first of all, we should always configure rollback authorization and rollback authentication controls in your clusters. So obviously there's specific components that we can deploy within our API server to make sure that we use RBAC authorization instead of ABAC. Or you can do specific different ways how you do that in your cluster, but I would always stick to RBAC. You can obviously discover and how you can do access over authentication. So again, if we're leveraging cloud deployment in our Kubernetes clusters, it's always easier to leverage authentication from your cloud store. So whether you use Kubernetes, which is now for example Azure Active Directory, which is now called Enter ID. So ideally you leverage that authentication store instead of configuring something different. You can leverage single sign-on as well to make sure that access and authentication it's seamless, and how you can leverage other specific controls that are within those authentication stores. You also have to think about how we do application secrets management and how do we encrypt them in etcd at rest, which I just mentioned previously. We also have to ensure that pods meet the defined pod security standards. How do we do quality of service and cluster resource management? So obviously, for example, when we think about deploying specific pods, we can also configure resource limits on the pods. So for example, to prevent attacks such as things like crypto mining and things like that, we can limit the resource on the pods, and how these resources are shared between the pods. We can also establish network policies, so cross-pod communication. That's a very important aspect, and it's very important to intimately understand how your communication within internal pods is going to happen, and what needs access to what. So network policies essentially allows you to limit the exposure. So if specific pods are breached and they are sending non-sensitive information, essentially, especially if you configure correctly network security policies, there is a good chance that you're going to limit the blast radius should a breach happen. So that's a great way to think about security. And then also TLS for Kubernetes Ingress, but not only for Kubernetes Ingress. There's a very important aspect to learn and understand how, we shouldn't just think about, using TLS at the ingress or traffic coming into the Kubernetes, but how we can deploy mutual TLS or MTLS within each pod communication and how we can encrypt traffic between every single pod. So that's another very important aspect to consider. I learned how to do that in deployment. So I'll cover some high level stuff and we can go probably a bit deeper in some episodes. But it's very important, I guess. If you guys want to upskill, consider Cloud Native. Framework. They have their own certification schemes, which are Certified Kubernetes Administrator and Certified Kubernetes Security Practitioner, which is CKA and CKS. So something to consider if you want to actually learn how to do these tasks, and be hands-on. But yeah, these are very important aspects to consider and think about how we can, deploy network policies, how we can deploy TLS, how we can, do rate limiting on specific pods and specific resources, and how we can limit exposure, how we encrypt our secrets. That's a very important aspect. So if we go into the next one, then the important part is how we can actually secure our containers and how we can provide container security. So this is another very important aspect to think about. So this is where we can use things like container vulnerability scanning and OS dependency security. So obviously we need to think about, as the kind of touched a bit earlier, on kind of two aspects. So obviously, first of all, we need to do a vulnerability scanning or our OS or our underlying host, as well as we need to do vulnerability discovery into our container images. And also obviously, it becomes a cumbersome task because depending on how you deploy, obviously, for example, if you use managed Kubernetes services, normally cloud provider will provide you with an up-to-date image that normally is not vulnerable, but you might potentially be running your own managed clusters, or you will be using your own images instead of using cloud providers. That's where container image vulnerability tracking and scanning becomes an important part. So making sure that you use the latest version. You're obviously making sure that any specific new vulnerabilities that comes out can be discovered and addressed into the next patch cycle. Another important part as well is you can set up now image signing and enforcement. So what I mean by that is, for example, I guess the big problems normally occur when we download or use either code or even images from an open source libraries. So open source libraries sometimes, allows threat actors or attackers to upload vulnerable images, or images that, potentially hold backdoors, can potentially, have exposed secrets that allows, potentially, threat actors to access them. So image signing essentially allows you to verify that the image comes from a reputable, and certified library, and also you can enforce that developers don't run away and bring some vulnerable images. So obviously, once you enforce the image signing, and you can whitelist specific libraries that are allowed to be used for image, downloading, you can limit a potential scope and potential risk of bringing vulnerable and bad images to your Kubernetes clusters. So that's one way to do it. You can also disable and disallow privileged users. So that's another part of your container deployment to understand is what kind of user can run the containers. And what I mean by user, I mean, as you know, guys, obviously when you work with Linux systems, you have a user called root. So normally by default your Kubernetes pods will run as root. But how we can limit, we can limit that and run them as users without extra privileges or root privileges. We can also limit what kind of pods are allowed, so we can create specific rules which prevents pods creating from if they are running if they are configured to be running as root. We can also configure that they don't have access to write to the root file system, and various other aspects. We'll talk about pod security context, which allows some of these things to be configured in later stages. And also the last piece is to use container runtime with strong isolation. So again, container runtime is built upon Falco and various other tools, and you can also implement AppArmor tools that allows you to detect undesirable events within your runtime, deployment, and prevent specific things from happening, and how you can configure making sure that your pods adhere to specific policies. So that's an important part in the runtime environment, how we can protect from nefarious processes from being created, how we can prevent pods from actually creating processes on the underlying OS, how we can limit the calls into the underlying kernel through sandboxing, using things like gvisor, and we can explore some of these more deeper topics in a various other episodes. I just wanted to give kind of an overview of the best practices and kind of the overarching thought about how we can secure that. And then the last part is obviously to complete the 4 C's is the code security. So we have to make sure that obviously every access is done over TLS. So if your code needs to communicate by the TCP, you have to make sure that it performs a TLS handshake with the client ahead of the time. With the exception of a few cases, encrypting everything in transit is very important. Going one step further, it's a good idea to encrypt network traffic between the services. So this can be done with a process such as, as I kind of mentioned, guys alluded earlier. So mutual TLS or MTLS, which can essentially perform a two-sided verification of communication between two certificate holding services. So that's very important. When you're building the pod-to-pod communication sort of network and how we can encrypt. So using something like mutual TLS, and obviously you have now tools which allow you to do that. So people worked with things like Istio meshes. Sorry, but Istio meshes also requires a specific configuration. So I know people use tools now like Linker-D, which allows you to straight out of the box to use mutual TLS. It's also important to limit port ranges of communication. So it's self-explanatory, but wherever possible, you should only expose the ports on your service that are absolutely essential for communication or for any metric gathering. It's also important to address the third-party dependency security. So it's very important to regularly scan applications' third-party libraries. So that's normally it's called software composition analysis, so understand where the software is composed from and what potential third-party libraries have exposure. Each programming language have their own specific tools, so it's up to you what you use. Obviously, OWASP has an open source tool which is called is essentially OWASP SCA. You also have to do making sure you do static analysis of your code. So most languages can provide a way to snippet the code to be analyzed for any potential unsafe coding practices. Obviously, this is the code how it's tested without being run. So it's a static analysis where you just check obviously for code and see that, making sure that the code's been built according to specific standards. So normally, static analysis are known to be giving you some false positives. So again, that requires some work to get the best out of the tool. So there's again various open source tools people use nowadays. SonarQube, I think always got their own tool as well that can be used for your open source analysis before you develop a specific. You might be thinking about how where to start, and then you can build on that way before you introduce enterprise grade tooling. And then again, you got dynamic probing attacks tools. So essentially, it's Dust. So Dust is similar to SAST. So SAST obviously is a static analysis. D is dynamic analysis, where you actually run the code itself, and then you try to, with a few automated attacks that can essentially try and exploit and see whether there's any SQL injection, cross-site scripting, cross-site request forgery, and various other attacks, which essentially tools such as OWASP, Z attack proxy or ZAP can help you do that, and obviously then you can elevate into the enterprise level tooling. So hopefully that gives you a bit of a flavor of what is the the 4 C's, what is the Kubernetes, what are the main things to be aware of when you start wearing into Kubernetes, and then we can go a bit deeper and actually how we can secure while deploying the the containers, the clusters. Actually go into a few more examples, actually looking at if you've never seen a YAML code, we'll show some examples how to build and configure network access policies, how to deploy specific runtime classes, how to deploy ARP configuration, how to deploy security contexts on a containers, how we can leverage as I say, limiting root exposure and running containers and root access to your file systems, and many more. We probably can even dive into how we can limit the resources and various ways how we can essentially limit the risk exposure into our Kubernetes running environment. Hopefully guys you learned something today, and obviously like and subscribe and follow to to learn more about Kubernetes secrets in the next episodes.